clearly didn't learn anything from the first morning. Let's try that again. Good morning, everybody. Good morning. Thank you. Okay, so welcome to the third and final day of ICAPS 2019. This morning I have the great pleasure of introducing our final invited speaker, Derek Long. I've known Derek for a very long time. I think we met in AIPS in 1998 in Pittsburgh. And, you know, back when the Earth's crust was still warm. Over the years, we've had plenty of arguments. We tend to agree on social and political matters, but when it comes to talking about temporal planning and numeric planning, we've had some extended arguments, I would say, a lot about representation. But I've grown to greatly respect Derek. Often, after one of these arguments, 3 days later, I will realize what he actually meant by something and what I should have said in response. But for the younger set in here, I wanted to tell you about a few of the things that Derek has done that still affect you. So back in 1998, or a little earlier, he was instrumental in the development of something called TIM, which did automatic analysis of PDDL domains and came up with state invariants and figured out typing for variables automatically. And that's, I think, probably the first instance of that kind of domain analysis in our field, and it's led to some other things later on. In the early 2000s, he was instrumental in the development of PDDL 2.1, which we all know about. And that was in service, really, of getting the first temporal planning competition started in 2002 at AIPS in Toulouse. And along with that, they had to build a validator. And so he was instrumental in the development of VAL, which has gone through numerous iterations over the course of PDDL development, but he's been instrumental in all of that. In 2005, I think it was, he was involved in the extension to PDDL3. So that's the incorporation of preferences into the language and constraints on goals. So that's still around and people are using it. And then shortly thereafter, they came out with the first description of PDDL plus, right, which people are using for continuous planning now. In terms of planners, back in 2003, they developed LPGP, which is, I think, one of the first planners to actually incorporate an LP solver into the process of doing the temporal reasoning and reasoning about heuristics. In 2004, Crikey was a temporal numeric planner that was ahead of its time in many respects. In 2009 was Colin, which was one of the first ones to take on handling continuous linear effects, numeric effects. And then in 2010, he was involved in the development of POP-F. So these are a lot of things that are still around and that affect all of us. Now, I always thought of Derek as a diehard academic and figured that he would die with his fingers frozen on the keyboard in front of him in King's College London. But somewhere along in late 2000s and 2010s, he got the applications bug. Mm-hmm. And he did some stuff on the ExoMars rover, modeling of that, on modeling of battery degradation over time and consumption, and then on power systems as well. And then in 2016, he really flew off the handle and left and went to Schlumberger. And I think he had somehow got the view that he actually needed to see if he could make the stuff that he developed over the years all work in a realistic setting. So he is going to tell you now about his attempts to become an oil tycoon and to squash us all. No, he's gonna talk to us about his application of some of this stuff to the oil business. And please give a nice hand to Derek.
Thank you. Okay, thanks very much everybody for turning up this morning on the morning after the banquet and last day of the conference, and in a special twist also before 9 a.m. on a Monday morning, which I think was particularly clever of the organisers. You run a tough gig for ICAPS speakers. Okay, so I thought I'd start off by telling you about what Schlumberger is, because it's a company that is very large, but often people aren't really aware of what it is or what it does. So it's a big company, Fortune 500 company. It's got about 100,000 people worldwide, so it's a big multinational company. Its revenues are about just under 40 billion a year, even now with the depressed oil prices. So I think that it puts it as one of the biggest companies in the world. It started in the 1920s as a family company, so it's named for the family that started it. Schlumberger is these two brothers, Emil and Conrad. They come from the Alsace region, which is why their name looks German but is pronounced in a French way. And they started in the wireline business, which is measuring geological formation by dropping tools down into a hole that's already been drilled on the end of a wire, which is why it's referred to as wireline. And they were at that time measuring resistivity and collecting data and telling people about the formation structures. And Schlumberger is actually one of the biggest holders of data in the world from geological survey data. It's collected huge quantities of geological survey data over the years. Obviously, the tools that were being used then have been improved, and wireline business is still an important part of what Schlumberger does. So, David's already spoiled my checkered past, so I don't need to tell you a lot about me. But I wanted to show you this recent photograph of me and Maria. So, I don't know if people know Maria, but this is Maria Fox, the most important person in my life, and the person that I have pursued all of the work that I'm about to describe together with her. So everything that I'm going to describe is work that she bears equal responsibility for. Okay, so let's move on to the actual business. So Schlumberger's one of its primary businesses is drilling holes, and this gives you some idea of how much it costs to drill a hole. So if we look at that graph, it's showing the lengths of holes, which is measured across the bottom of that graph, running in meters on the main measure at the bottom there. So you can see that a lot of the holes that are being drilled are about 3 or 4 kilometers deep and range down much deeper, down to, on this graph, about 10 kilometers. I think that the longest wells that have been drilled are more like 16 to 20 kilometers now. And on the other axis, you're seeing price, how much it costs to drill a hole like that. So for a typical 3-kilometer hole, and that's a pretty standard oil well or gas well drilled in, for example, the Permian Basin, which is in Texas, one of the biggest oil reserve areas in the world. That would cost you about $7 million. So obviously the question is, who's willing to pay that much money for a big hole? And if any of you are interested, I'm sure if you see me afterwards, we can negotiate some reduction. But otherwise, I guess the people that we're mostly selling to, the oil and gas industry, of course. And one of the things that I think is surprising, I mean, this certainly surprised me when I first discovered it, is just how much drilling is going on. So even now, even despite the rather depressed prices of oil, 300 to 400 wells per month are being drilled just in the Permian Basin in Texas. Okay, so that's an enormous activity. And one of the reasons, of course, is that shale gas has changed the landscape a lot. So a lot of that drilling is looking for shale gas, but not all of it. I mean, much of the drilling is still for oil or for regular gas supplies. And globally, about 100,000 wells or so per year. And you can see this projection of numbers of wells that are expected to be drilled. It's not going to fall off anytime soon, at least according to the projections. Whilst we still want the products that come out of those holes, people are still going to put the holes in. So, when oil prices started to fall in the mid-2000s and dropped down, so initially they dropped as low as under $40 a barrel. But even at $50 or $60 a barrel, it's quite a tough market in which to make competitive oil production profitable. And one of the ways that people were interested in trying to improve the profitability of the business was to improve the drilling efficiency. So basically producing these wells in a kind of factory style, so manufacturing wells, seeing it as a manufacturing process. And a lot of companies started to think about what role automation might be able to play in trying to achieve that. So drilling a 3-kilometer well in the Permian Basin, which is a reasonably straightforward formation to drill in, would typically take about 3 weeks or so, assuming that everything goes according to plan. But it's quite a long tail distribution for the time, and you find that there are some wells that turn out to be troublesome for one reason or another, often due to human error, but sometimes due to other natural problems, and so sometimes it will take much longer. So one of the key objectives is really to reduce the variance on the time it takes to drill a well, rather than necessarily to reduce the actual time it takes to drill a well, although clearly that would also be helpful. The oil and gas market is not the only group of people who want holes, and one of the areas that Maria and I have got particularly interested in and been trying to promote very strongly within the company is the drilling of geothermal wells. So you might have come across geothermal drilling. So geothermal drilling is drilling in order to get typically to hot water, but into heat at least. And the way that it usually works is for deep geothermal wells, and there are a variety of different types, but for deep geothermal wells, you would typically drill 2 holes, one of maybe 4,000 or 5,000 meters, and another shorter well, typically maybe 2,000-3,000 meters. And then you inject cold water in through one of the wells, and you allow it to seep through the fractures in the rock between those 2 wells, so that when you receive the produced water at the other end, it has heated up. And the objective is to get it up to high temperatures. If you can get it up to 70 or 80 degrees Celsius, you consider that low-grade heat, and if you can get it up above that into steam kind of temperatures or superheated steam, then it's obviously very high value. And one of the things that makes this particularly challenging is that usually the formations that you're drilling into are much harder formations than the formations that make up the Permian Basin, for example. So that 5,000 meter well there, for example, in the kind of formations that you might be drilling for a geothermal well, instead of taking 3 weeks or 4 weeks or whatever, would probably take you 4 months or so to drill, because it just is a much harder and much more arduous job. So just to give some sense of the scale of geothermal energy use across the world, it's not an energy source that people are often familiar with, but it has been deployed increasingly over recent years because it's a clean energy and a base load. You don't rely on the weather for it. It will generate energy continuously and consistently throughout its lifetime, and its lifetime is usually limited by the materials that you use to line the hole or to make the various components of the well, rather than by the energy source itself, which is actually radiation driven from materials in the Earth's surface there. Okay, so this is one of the biggest geothermal power stations currently operating. So it's a 250 megawatt power station that's operating in Kenya. Kenya's been driving very hard for geothermal, so it's got about 50% of its energy now coming from geothermal. So it's quite a significant proportion of what it is using. 250 megawatts, just for people who don't really have much sense of what scale that is, that's about a quarter of the size of a moderate-sized coal or gas or oil-fired power station. So it's not huge, but it's comparable size, and certainly it's extremely interesting to see a power station that size operating on geothermal. This is, I hope, just about legible, but it indicates where in the US geothermal resources have been exploited, and you can see a lot of geothermal has been exploited around the western seaboard of the US there. And of course the reason for that is that that's where there's the most interesting geomechanical activity. That's the source of a lot of the energy that's being harvested. So that's why you tend to see this kind of geothermal stuff being drilled into areas where the activity is close to the surface or relatively close to the surface. Just to give a sense of how big the capacity is across the world of geothermal. So you can see that although Kenya has a huge proportion of its energy being generated, and most people, when they think at all about geothermal, tend to think of Iceland as being the key player in the field. This graphic just illustrates that actually the US is by far the biggest installed capacity of geothermal generation, so it's a very big market in the US. And actually Iceland is after Italy in terms of size of its geothermal generation. So Italy is actually quite a big player in this. Of course, it has access to quite a lot of volcanic regions which generate a lot of energy. And Europe as a whole is really pushing very hard for geothermal energy. So here's a rig drilling deep geothermal well in Basel. I thought that this would be interesting because obviously working in Basel it won Best Paper Prize. So this is working actually in the city, and it's one of those things that makes geothermal drilling quite interesting, that very often the richest areas of geothermal opportunity are areas that historically humans have found desirable places to live. Because there are often spas near the surface or hot water pools or whatever, and so those things may mean that you're often drilling in areas where humans, or it's sort of urban area, humans are inhabiting areas around you. And that constrains the kind of drilling operations you can perform, which is an additional source of interesting constraints there. Although Europe as a whole is putting a lot of money into geothermal drilling, you're probably aware that the UK is exploring other ways of getting into deep hot water, which are very different. So, for those of you who saw my Spark talk last year, you probably remember some of this, so treat this as revision, and those of you who haven't seen it before, it is on the exam, okay? So this is how we drill today. This is basically how drilling has been done for quite some time. It's an old industry, and drilling hasn't changed an enormous amount in terms of the basic techniques that drive it. So a drilling rig is placed over the spot where you want the hole. It provides the framework that's going to support the drill string, which is the sequence of pipes that go into the ground and hold the bit, which is actually the drilling bit at the bottom of that series of pipes. It will provide the motive power, so it's going to torque that drill string in order to drive the drill bit. And there is an important second part to this, which is the fluid circulation, which here is referred to as the mud pumps and mud pits. So the mud pits are where the fluid that comes out of the hole is stored so that it can allow the rock chippings and what have you to sediment out of the fluid that's coming out of the hole. It's then pumped round and back down into the hole. So this has several roles to play. One is to bring out the cuttings that you're generating at the bottom of the hole. You've got to get them out of the hole so that you can keep the hole manageable. Another of the roles is to cool the bit, because obviously you're generating a lot of heat. the friction of cutting through the rock is generating a lot of heat. But also an important role is you've got to balance the pressure of the overburden, the rock on either side of the hole that you're drilling. You've got to hold that weight back, otherwise it will crush the hole, collapse into the hole and crush it. And so the hydrostatic pressure of the fluid that you're putting into the hole is important to just maintaining the integrity of the structure that you're drilling. And often that means that you have to be very careful about the design of that fluid so that it provides the right density, and we'll talk briefly about that again in a moment. So this is what a drilling rig floor looks like. You can see that it's full of big pieces of heavy equipment. It's got big, heavy guys that will manipulate that equipment using large lumps of dumb iron in order to push pipes together and lock them by screwing them together and holding those pipes in position and so on. So it's a dangerous job. It's a very physical job. It's a dirty job. It's often in inhospitable places. So it's not a job that's particularly pleasant. And you can see that on the left there is one of the most, what I would consider one of the most frightening of the jobs on the rig, although they're all pretty tough. This is a guy on what's called the monkey board. So that little platform that he's standing on is the monkey board. And his job is, so this is a rig typical of modern design where the top drive, which is the motor that's actually going to drive the drill string, is suspended on a block and tackle, and you can see there it's suspended above his head. And his job is to grab the top of the pipe, which is being swung into position, and lock it into the holder on the bottom of that top drive. So he has to sort of leap out and grab the top of the pipe and swing it into position. You can see he's suspended on a bungee cord there to make sure that he doesn't fall too far if he loses his footing. But it's a really frighteningly unpleasant job. It's carried out, drilling goes on 24 hours a day, rain or shine, so it's carried out in much worse conditions than that suggests. So it's a pretty frightening thing. And the service of all this is in building the construction of a well like this. And one of the things that also amazed me when I first started learning about this stuff is that you can make these holes go in all sorts of crazy shapes. So that's quite a normal shape where you drop down on a vertical and then you dogleg, you curve, and then you go into a lateral where you're drilling into the reservoir. And usually you want to approach the reservoir on a lateral because the oil-bearing rock is a layer in the structure, and so you're really interested in getting your liner, which is going to allow you to extract the oil into a long stretch of that reservoir in order to collect as much oil as you possibly can, or gas, of course, if that's what you do. So why is this job so hard? I've given some hints about that, but what I wanted to talk about is what, in the industry, when people talk about planning a well, and I should emphasize that there is a lot of planning before we even get to the point where we're planning the construction of an individual well. So David and I were talking last night about the fact that before you decide that you want to drill a well, there's a lot of decisions about where you want the wells, how many wells you're going to want in order to tackle a particular reservoir or a particular collection of reservoirs, where the appropriate infrastructure might be on the surface that you can tie back to, and so on. So there's a whole load of decisions that have to be made that can be seen as planning or planning-like decisions that come before we get to the point of constructing an individual well. But let's focus here on the construction of a single well. So the first thing, or one of the first things that people will be thinking about once they've decided that they're going to build a well and they've decided where they're going to build it, is what trajectory they want that well to follow. So I showed you the trajectories that are pretty common, the dogleg trajectory. So you can see over there that's a Norwegian well design that was being used a few years ago, which has a very long lateral. That lateral is about nearly 3 kilometers long. The vertical is about 1.5 kilometers. So this is, a reasonable sized well, but you can see that a lot of that well is being drilled actually horizontally. And then the well design on the left is a much more crazy design of well, which involves a sort of large corkscrew of the drill bit round formation structure in order to get into the position that they want to for the reservoir. So you can see that these well designs can be quite complex. The geometry of them is not always the same. They vary from well to well, and each one is typically unique. One of the next things that will be thought about is the casing design. So when you drill a well, you're obviously drilling into bare rock, but what you want to be able to do is to end up with a sealed off tube into the ground that has a liner which is made out of steel in the first instance, and that's the casing. So the casing plan decides at which points in the construction of the well will you pause the drilling process in order to put the first stage or whichever stage of liner that you're going to put in there, the casing that you're going to put into the hole. And then you will cement that in place before you start drilling the next section of the well. So the well's usually built in sections, maybe 3 sections would be a typical design, and each section will be cased before you move on to the next section. And deciding where you're going to put those casing shoes, the bottoms of those casings, is an important part of the design. Part of it's to manage pressure in different formation structures, which I won't go into, but that's part of the reason that that's a complex problem to solve. And then you've got the mud plan. So once you know what the formations are that you're going to be drilling into and what the objectives are going to be in terms of casing shoes and so on, you'll now have some idea of what density of fluids you're going to need, and that will require typically some sort of chemist to come along and help you to decide what you're going to put into the water that you pump into the hole. You will often be using barite, which will weight the water to give it higher density so that you can hold back the weight of the rock. You'll probably be putting in some pH controls and such like in order to give it, and some gelling agent maybe, and stuff like that to design this fluid to make sure it can do the job. Then you're going to design a bottom hole assembly. So bottom hole assembly is the structure of the part of the drill string that you're going to put into the hole first. So this is going to be the bit, obviously, at the very bottom. But above that, there's a whole assembly of components, and the precise design of that depends a lot on what you're trying to achieve with your drilling process. So there will usually be some stabilizers to try to keep the whole drill assembly in a correct alignment with respect to the hole that you're trying to drill. There'll usually be some reamers, which are tools that allow you to clean up the hole as you're drilling it. And often there will be some measurement tools, some kinds of measurement tools to allow you to track information about the formation that you're going through and so on. I should emphasize that communication up and down a well is basically impossible for most of the time. Most of the time there is no link between the bottom hole assembly and the surface, because the conditions in the hole make it impossible to really set up any kind of communication infrastructure. You can communicate very, very slowly using what's called mud pulse telemetry. So when the hole is full of fluid, you can pulse the pump rate, and assuming that your tools are smart enough to understand what codes you're trying to send them, you can communicate at about a bit a second or so down the hole, and then they will communicate back using the same technique back to the surface. So it's a very, very slow way of communicating data. So you can't really use these tools for generating an enormous amount of surface data, and you certainly can't do any kind of control from the surface using these techniques. You're basically relying on, well, a lot of human experience and various surface measurements to try to understand what's going down at the bottom of the hole. And then finally, after you've designed your bottom hole assembly, you'll start thinking about the actual drilling process, which means you're actually going to build something that looks very much like a plan. In fact, the sort of thing that we would construct. And here is a plan. This plan actually was built by one of our planners, built by Popper, using a model for the well construction. So this is what the kinds of plans would look like at this level of abstraction, where we're talking about drilling as a single unit activity to drill an entire section of the well. So this is a 3-week-long plan for construction of a 3-section well plan. But that wasn't actually the area that we were involved in at the when we started with the company. The thing that they were interested in is something that is usually called drilling slips to slips. So I'll just explain what I mean by that first of all. So when you build a well, you're typically using these lengths of pipe that are made up out of 3 pieces of 30-foot length pipe. So a typical length of one of these pieces of pipe is 90 feet or so, 30 meters of pipe. And you can see a whole bunch of them racked up there against the rig. And the reason that you would do that is that the rig size, which limits the total length of the pipe that you can suspend under it, is a limiting factor. And they're usually about 100 feet tall. So that limits the length of the pipe that you can handle inside the rig. Some rigs are smaller, and so you might not actually be able to run 3 joints of pipe inside a single rig if that were the case. And obviously it would be convenient to be able to run bigger lengths of pipe because it's more efficient if you can run the drill for a longer period of time before you have to pause to fit the next piece of pipe in. So it's more efficient if you could drill longer pieces, but you also have to think about shipping the rigs and the pipes around the country. So the scale of the low loaders and the materials that you've got to carry is also a constraint. So this is what you basically end up with. And between drilling those lengths of pipe, you will basically hold the drill string off the bottom of the hole, and the weight of, so each of those pipes weighs about a ton. So if your pipes go, let's say, 20 or 30 pipes deep into the ground, you've already got 20 or 30 tons of steel just suspended there. You're going to have to hold that off the bottom of the rock in order to avoid crushing the rock, and the way that you do that is with these slips. So these are big iron wedges, and roughnecks, the guys that work on the rig floor, will, when the pipe has been brought up to what's called the stick-up point, the point where it's ready to have the next pipe connected to it, they will drop these wedges in place in order to hold the pipe in place so that they can now disconnect the top drive and put the next pipe in place. And this is a very manual process. This involves people with big muscles that are going to have to be able to shift big pieces of weight around. Whilst you're actually drilling between those slips to slips, so between the points where the pipe is suspended in slips, you're going to be controlling the weight of the bit on the bottom of the hole. So that's the schematic there on the right. You're suspending that from the block and tackle on the top of the rig. So you're basically lifting the weight of the drill string, and you're allowing just enough of the weight of that to rest on the bottom of the hole to allow you to get some force to be able to drill with, but not all of the weight of it because you would crush the rock. So you're kind of lifting the weight of the drill string, but just allowing it to rest a little bit on the bottom. And then you're going to be spinning it, so you're putting torque into the drill string, and you're also controlling the fluid. So you've got several things that you're balancing together. You care about balancing the pressures that you're generating from the fluids, the weight that you're putting onto the rock, the torque that you're putting in from the top, how quickly you're rotating the drill string, and so on. So one of the things that I found particularly interesting when I started in the industry was this question of how you actually manage to make a steel pipe which is about 5 or 6 inches in diameter, so it's a large, serious steel pipe. How you actually make that go around corners seems like it's not really very realistic that you could drill these strange shaped wells. The way that people control the direction in which they're drilling is, well, depending on the modernity of the well, of the rig that they're using to drill the well, they might use equipment like this. So this is reasonably modern kit for drilling round corners. So what you would have is what's called a mud motor, a hydraulic motor there in the figure. So you put a motor at the bottom of your bottom hole assembly, which will be driven by the energy that you're putting in through the fluid that you're pumping. So you're pumping fluid through that motor, and that will drive the motor. And that will allow you to make the bit turn even though you're not turning the whole drill string. So you can hold the drill string still, and allow the bit to turn at the bottom, which is very important because obviously if you had to rotate the drill string at the same time, it's much harder to work out how you would make it actually turn a corner. So you're going to allow the drill string to point in the direction you want to drill and then just rotate the bit at the bottom of it. And the way that you get the drill to point in the direction you want it to go is that you well, one of the ways that you can do this is you might use these hydraulic actuators, which are like pads near the bottom of the bottom hole assembly, near the bit, that you can control to force the bit to point in a particular direction away from the rock. And you're talking about very, very small angles, maybe 1 degree deviation. So these are tiny angles that you're getting it to turn through. So the reason that you can manage to turn so far is because you're drilling a very long well. So to give you some impression of, because I find that kind of physics very weird, and the impression that I think gave me a better intuition about this is if you think about a catheter, so this is a heart ablation catheter, typical heart ablation catheter which a surgeon would feed through the artery from the groin up to the heart is about 2 to 3 millimeters in diameter. That's the typical size of one of those catheters. So a drill pipe's about 15 times that diameter. So if you're drilling a 3,000 meter deep well, it's like having a 200 meter long catheter that you're trying to reach the patient with. So that gives you some idea of why you might expect enough flexibility to be able to turn weird corners and so on. If you had a 200 meter long catheter, you would imagine that it would be pretty bendy and you could do stuff with it. Okay, so when people started thinking about automation, one of the big challenges in the field is there is a lot of legacy equipment, a lot of stuff that has been around a long time, and it's all very expensive kit. People aren't willing to just throw it away, so you can't simply say, well, let's start with a clean sheet and design a new piece of equipment. You basically have to imagine working with what's already there. Fortunately, I've never seen anything quite like that in the field, but I'm sure that there are still operators using things not far off. But of course, as you start to look at more modern rigs, you find that there are opportunities for improvement in automation. So you'll get more effective sensors, you'll get more effective collection of components that are actually automated. So some of those operations that I showed you on the rig floor that involve using slips or joining the pipes, making the connection between pipes, some of those things on a modern rig might be automated. It won't be on very many of the rigs because there's a huge collection of equipment that's been around for a long time, but on modern rigs you will find that those things are automated, and obviously if it's there you would like to take full advantage of it, as well as being able to keep an eye on the legacy equipment that you also will need to be able to handle. So the goal then of this whole body of work is basically to coordinate all of these components on these rigs in order to safely drill initially just one length pipe, slips to slips. That's the goal. I just wanted to start this video for you. So this is a rig that's showing automated pipe handling. So this was a rig that Maria and I went to see that's operating in Cornwall. This is actually a geothermal well that they're drilling here. And because it's in an urban environment, they were very conscious of the need to maintain quietness, so they chose this specific rig for the reason that it does this automated pipe handling. So it offers this relatively very quiet handling. If you've got all the pipes racked, as you can see on the right-hand side there, if there's any kind of wind, all those pipes rattle at the top and there's a lot of noise. So in order to avoid the noise, this was actually in an industrial park right on the center of the city, so it's had very tough constraints on how quiet they needed to be in operation. So one of the things I wanted to emphasize, just as we're watching the last bit of that video, you saw it swing that pipe in, and just as the pipe comes into position, you see the top drive begin to move up in order to attach to the top of that pipe. And so this is not an automated rig in the sense that all of these operations are being carried out by teleoperation. The 2 humans on the rig operating the pieces of equipment, the pipe handler and the drilling equipment. And there is considerable inefficiency in that interaction because the top drive could have been moving whilst the pipe was being brought into position, but in fact the driller left the top drive at the bottom of the stand there until after the pipe had been brought into position and then brought it up. And that's an example of how that kind of teleoperated human interaction can lead to inefficiency. And it's important because when they were drilling this well, because it was granite, they were going through bits very quickly. So they were drilling here a 5,000 meter well, and in the first part of that well, they were having to replace the bits about every 250 meters. So very, very frequent bit change. And every time you want to change the bit, you have to pull out all the pipes, disassembling them one at a time, rack them up, and then change the bit, and then put them all back down the hole again. And all of that is flat time. You're not drilling during that period of time. So that's a very inefficient period. And if you could do it more slickly, if you could operate that whole process more efficiently, you would be able to save potentially quite a lot of time in the construction of the well. Okay. That's a picture of a more sophisticated well. So this is a rig called the T1000, which is a Schlumberger's rig, fully automated pipe handling and fully automated rig floor, and equipped with a very large collection of sensors. It's probably got the most sensors on any rig currently deployed, and that's capable of automating vast quantity of the drilling process, capable of in the sense that all of the machinery is in place to allow you to do those things automatically. Okay, so now let's talk a little bit about automation and how the work that Maria and I and others have contributed to this fit in. So what has planning got to offer? Before we joined the company had been working very hard on automating slips to slips, and they had a lot of problems with it. The problems were that they tried scripting the sequence of activities, because on the face of it, it looks as if when you drill a length of pipe, it actually is basically the same thing that you do every time. It looks on the face of it as though that's the case. What they found is that actually it isn't like that at all. Almost always something will happen that you didn't anticipate. Almost always you will enter some new failure mode where the failure might not be a real failure, but it's just a failure in the sense that you hadn't anticipated this particular state, you hadn't written a script for what you should do when you enter that state. And the joke at the time was that when they tried testing this, they needed twice as many people on the automated rig as they needed on a manual rig, because they needed all the software engineers there to pick up the software when it fell over because of one of these missed failure modes. So it really wasn't a very effective solution, and in order to try to cover more and more of these cases, they were extending the script with more and more contingencies and trying to identify more and more different states, and the code became both impossible to maintain but also impossible to trust. Nobody believed that it was capable of doing the job that it was supposed to do anymore. I just want to give you some sense of the kind of weird things that can happen on a rig, not particularly good things. So this is not the old lady in a wheelchair with the broom chasing the duck, but it's the same kind of phenomenon for the rig. So what you can see here, before I run this video, I'll just show you what's starting off so you know what to look out for. This is a fire that started on a rig site. It's not actually a fire that's related to the oil. It's actually a diesel tank that was being stored on the site that has caught fire. So it's human error, because obviously you should be maintaining safety over these things, but okay, so we have a fire. Slightly more significant human error is that there is a crane positioned next to the surface of the rig, which shouldn't be on site at that point. And you can't really see it, but to the side of that crane is the top of the rig, which is a pressurized well, and so there is a big pressurized control system on the top of that well with a choke that's holding back the pressure of the fluid inside it. So, oops, sorry, let me just... Okay, so the fire is difficult to control, and unfortunately it causes the crane to collapse, which knocks the top off the well, and now a lot of pressure is being released from that well very suddenly. And in a moment, you should begin to see that the well is ejecting all of its contents, and that includes the steel pipe and the bit. And so in a moment, we'll swing the camera up, and you'll begin to see that so I hope you can see that the pipe is spiraling up there into the sky. That is steel pipe that is being thrown out of the hole by the pressure of the hydrocarbons, particularly in the hole. And shortly you will see the bit, which, whenever you write a model of the drilling domain, your first assumption is that the bit will always have a positive depth. That is... okay, so one of the advantages that planning has to offer, and actually one of the things that was particularly gratifying, was that people in the company had begun to explore and had identified planning as a possible solution to their problem before we came into contact with them. It was kind of a lucky coincidence that we came into contact with them through another means at the same time. They'd begun to realize that maybe planning would be a way to solve this problem of how do you deal with the dynamic situation. So it's not that the goal is changing. The goal is always, if you're drilling slips to slips, you still want to get to the same place. But the problem is that you're often starting from a new initial state. You didn't expect to be in this state. How do you resolve the question of getting from this particular state to that goal? So dynamically generating the plans, or if in some sense dynamically rescripting, I guess, from the current state in order to get to the same goal at each point in the construction of that to that particular drilling slips to slips. So the targets here are consistency. We want to be consistent drilling each length of pipe, obviously being safe, efficient. Another thing that I'll come back to a little bit later on, but an important thing that became apparent over time is an alignment with standard procedures, and then also the target here is to reduce that non-productive time, reduce the time that you spend just manipulating pieces of equipment but not actually drilling holes. So what did we bring to the problem? Why were they interested in talking to us? Well, crucially, you're having to coordinate activities across time. So the first and most important part of the problem that they wanted to be able to think about was a temporal problem in which you're coordinating the interactions of different pieces of equipment and making sure they converge at the right times on particular activities that they're performing. And so temporal planning was the thing that really drew their attention. They were particularly interested in that. And of course, looking at temporal planning, they did come across our names because, as Dave mentioned, Maria and I spent a lot of time thinking about temporal planning back in early days of our careers. And PDDL2 is a very useful tool for describing these kinds of problems. And we had planners that can manage this kind of stuff, built by us and Andrew and Amanda Coles, who contributed to all of these projects. So that was what drew them in, but actually one of the things that particularly interested them and was also very gratifying for us was that they were particularly interested in being able to model continuous change. And linear continuous change was exactly the kind of continuous change they were most interested in. So if you're drilling, your simple model, at least, is that the depth of the bit is going to be increasing linearly over the time that you're drilling. I mean, that's a reasonable enough assumption for most of the activities that you're performing. And some of the activities that you want to perform whilst you're drilling include things like turning on some of those tools or managing some of those tools to perform some measurements in the hole. And those things will happen in parallel with drilling. You don't want to stop drilling whilst you do that. You want to just carry on drilling. And so you're typically going to be setting up constraints based on depth, but those need to be translated into time based on the measurements of the depth that you're expecting to be at particular times. So this is how continuous change can play a role. Of course, you need to be able to model, and one of the things that has been very interesting in taking this work out into industrial application has been seeing that when you start trying to get people who want to approach planning as a tool for solving a problem rather than as a basis of their research interests, they don't care how you do the planning, they only care how you get the planner to do things for them. And the way that they interface to the planner, of course, is through the models that they have to construct. Fortunately, we're talking to engineers, so they're technical people. They're not frightened of having to build models, and actually they find PDDL quite accessible as a way and reasonably intuitive as a way of getting into these. But what they did find difficult was the lack of tool support for doing that. And you will have seen over the last few days that Jan has been very active in building tools that help to support this process and trying to convey those tools out into large parts of the company, making it possible for people to build and maintain and manage these models that can get quite large. So just to give some sense, model for drilling slips to slips, our current models are about 40 action schemas. They have, 50 predicates or so and about 20 functions. And plans can vary, so it depends on where you are in the drilling process, and also it depends slightly on the ambitions that you have. But you might be drilling for just a few actions, or it might be hundreds of actions, depending on precisely what it is you're trying to achieve. And well construction model, that was a model that got constructed a few years ago initially and has been developing since then, is now a very large PDDL model, about 4,500 lines of PDDL and more than 100 action schemas. So these challenge the ways that we have thought about PDDL models in the past, and I think that trying to think about how do you see PDDL modeling as part of a software engineering enterprise rather than simply a research exercise is an important question. So another thing that has proved interesting for us from the work that we've done in the past and conveying it into this context is some of the problems that you need to solve whilst you're drilling include managing physical constraints that are not linear. In fact, they're much more complex. One example is the rate of penetration optimization. So you're interested in optimizing for weight on bit and RPM, torque. What should you choose in order to maximize the rate that you go through a particular rock? So you know what the formation is, and you're interested in trying to optimize that. And that's a nonlinear optimization problem, and there are obviously optimizing tools for solving that problem within the company because it's something that they've been thinking about for a long time. So what you want to be able to do is to hook into that and say, can you tell me the answer to this question? And one of the places that we found a good solution to this problem is in the work that Chiara had been doing with us a few years ago on linking an external solver to a temporal planner. So another of the problems that we were encountering immediately that we started working with the company is how do you take a plan? It's easy enough to think about generating a plan, but how do you take that and turn it into actual execution? And obviously, if you think about a PDDL2 plan in its classic form, it's really rather brittle as an artifact for execution. If you imagine trying to use the times of these actions as the basis for execution, you can see that, I mean, these times have been computed based on some of these linear function solutions. It's really not going to be practical to treat that as an artifact to be executed literally. Unfortunately, we've been doing some work with Dan and Michael and Bram and others on thinking about execution in various contexts and had developed this ROS plan system, so we had a lot of ideas about how to achieve that. And we're interested in really looking at the causal structure to drive the execution of the plan rather than just the times at which we expected things to happen. So when it comes to plan execution, there are several stages, and I mean this is familiar to most of you, but one of the new problems that we encountered in this context is that the various parts of this stage are going to be deployed in different places. So the planner might be deployed, for example, in the cloud, but certainly on servers locally on the rig at the very least, possibly in town, whereas the actual control structures further down, the dispatcher is going to be local, and then the control structure is typically going to be on PLCs or something similar on the rig, and then you're right down to actuators. So each of these components is typically very separated from the others, And you have to think about how you're going to protect yourself from failure in communications along this chain as you dispatch a plan. So when you think about dispatching a durative action, you really have to think, if I start this action, but I lose communication before I get to finish it, what's going to happen? How am I ensuring that this action is going to finish? What initiates the control signal that will terminate that action? And who takes responsibility for it in this chain? How can I guarantee that I'll end in a safe state? So this is another observation that we made that's less relevant to drilling slips to slips, but some of the other problems that we've looked at. Sometimes you can't dispatch the actions that you care about executing purely on the basis of observable signals. Sometimes you have to execute based on time. So this is an example. If I need to get a logistical support team in place to support an activity after the activity I'm currently executing, when should I ask that crew to set off to come and join me? I don't want them on site early because I'll have to pay them to stand around idle. So I really want to get them to set off at a time that is based on anticipating when my current job will finish and how long I think it will take them to get to that job. So that means actually that nothing will happen in the world that tells me this is the point at which I should ask that crew to set off. It's based on time. So I'm still going to be driving some of my execution based on time. Okay, I just want to finish up by talking about where we actually have reached. So just to give you some sense of the achievements that we've made. So when we joined the company in 2016, we'd actually been working with them for a few years before that in consultancy mode. And in 2016, we successfully field tested our first plan-based drilling system on a client's rig without any software people there to control it. So this was the first time it was operated purely by the drillers with no software engineers there to support them. You can tell this is a driller because you can see 2 hands, but you can only see 4 fingers. So this is a sure sign that it's a real driller. So this is the driller interacting with the driller's screen, which is where they would normally control a lot of the systems that are under their control. And what they're actually doing in this particular shot is releasing control to the automated system, which runs on a separate, or is illustrated on a separate screen. So this is the screen where they set the goal. So they choose the goal. In this case, they have a limited palette of goals. And then off goes the process. So I'm going to just quickly run this. This is a video. This was a relatively recent video of the thing in operation. There's no sound, unfortunately, but maybe that's fortunate because the drillers are so happy about this. They're singing, and drillers singing is definitely something that you want to avoid having to listen to. But one of the things that makes it very interesting to us is to see how relaxed and how happy they are to leave the control to the system and just let it do its thing. So this, just to show you that screen a little bit more closely, on the left you can see the plan that's being executed. On the right you can see a context screen that shows you what the context is for the execution of that current action. And just down here at the bottom left you can see which the 4 subsystems that this system will take control of, which of them is currently under the automated system's control. In this case, all of them. The driller can choose which ones to take out of the control of the system according to their particular preference. If they don't trust the system or they're not liking what they see, they'll remove control. So we don't offer an explanation. They don't care about having an explanation of this particular plan. If they don't like it, they just won't let it do it. They will do it themselves. Okay, we are currently operating now in 3 countries. We're expanding across multiple rigs. This year is a big year for deployment. I think one of the most significant successes for us this recently was operation on a client's rig. So none of the team were there. It was purely the client operating it, and they were able to drill what had previously, for human drillers, been an 8-day, 2-run drilling section. They were able, for the first time ever, to drill that in 5 days in a single run. And the reason is because the planner is planning very, very precise and consistent operations. Everything is being followed rigorously. There's no human driller in the loop that's trying to push the tools a little bit harder because they think that locally optimizing will globally optimize. They are not in the loop for doing that, and that means that we can get better achievement of performance overall. I'm going to just skip across this because I think I'd like to just talk briefly about this before I finish. So one of the things that's a major challenge as you deploy this kind of system is validation, constraint, the trust and the building of trust and the constraints that you need to put on the plans in order to make them trustable for humans, and how explanation plays a role. So one of the things that's interesting is that at the beginning, when you're first automating, your target is to reproduce what the human would have done. They need to believe that you can do what they would do, even if it's not necessarily the way that you would choose to do it. That's your first target. And that means that sometimes you have to impose constraints on the models that force the path of the planner in a direction that wouldn't have been its first choice. As the trust is built, the human steps back and is very often then uninterested in how you're actually performing the task. They just trust you to do it. Now the driller will press the button and sit and read the paper and put his feet up. He doesn't care how the planner is actually executing this plan. However, there are some constraints that you have to meet. These standard operating procedure constraints, these are kind of legal constraints or operational constraints imposed by the client that say, you must do things this way. It doesn't matter whether you could have found a better way or you would have liked to have done it a different way. It's just the way that we do it, and that's the way you're going to have to do it. So one of the things that challenges us at the moment is trying to think about how we can use the trajectory constraints of PDDL3 or PDDL3-like constraints to express some of the constraints that we're interested in. Some of these constraints are really based on action relationships, and that is something that's harder to currently express in PDDL3 than we would like. Okay, I'm conscious that time has run out, so I'm going to stop. I'm just going to say some of the lessons that we have learned that I would like to share are things like time and numbers really matter for planning in application, and also it's modeling that matters for users, not how the planning is actually done. And PDDL has not proved to be at all a barrier. And we're deploying it across other areas of application in the company. So on the left is an application in wireline, on the right is an application in sand logistics. So we're seeing a whole bunch of new applications coming. I have to say that still, even so, when we talk to senior managers, they still assume that what we're doing is machine learning. It's a very hard sell to tell them that actually it's something very different from machine learning. It's just the way that the world is at the moment. When Chris put up a big slide with final words yesterday, I thought, wow, that's quite portentous. I'd better think of something important to say myself. But
Okay, so we're definitely running late, but I would like to give you guys a chance to ask a couple of quick questions, and then we'll start the next session a few minutes late. We got tons of questions. I think you had your hand up first.
So thanks. This is fascinating. One of your motivators was handling failures, right? And you're still using a deterministic planning formalism. So can you say something about modeling the uncertainty and planning for it?
The uncertainty that we're looking at, you saw in that video clip, is that the breadth of possible events is huge. I mean, there's just really no way that you can anticipate what might happen. So rather than trying to anticipate those things, and rather than trying to plan in advance to avoid them, which in general for those kinds of situations is impossible, what you're really thinking about is, what will I do when things have happened? Things will always fall outside my expected envelope of performance, so how will I recover from that? And so clearly you could imagine trying to treat the problem as some massive POM-DP and maybe partially solve that and try to explicitly represent some of the uncertainty in the problem. But actually, the trajectory of states that you really care about and that you visit is very narrow, and you're really most interested in getting straight back into the path that you were originally following. So what we've found is that replanning works extremely well for us. That's the way that we've tackled it. It hasn't proved to be a problem. We have to be able to respond to whatever the events are with a new plan within about 10 seconds maximum. So we have to be able to generate these plans fast, and we do. I mean, we've now drilled thousands of stands, so it's currently, that has worked well for us.
Great talk, Derek, and very nice planning domain. My question is, how much of the interaction constraints are taken into account at the planning level to allow the driller to intervene while dispatching and so on?
So, very, very briefly there, I didn't really have time to go into it as far as I would have liked, but I showed you that those control buttons at the bottom of the screen allows the driller to change which parts of equipment are available. And one of the challenges, again, I didn't have time to talk about it, is we're deploying the same control system on rigs that we own, but also rigs we don't own. And on rigs we don't own, we can't guarantee that they will have all the same sensors. We can't guarantee that they will have all the same actuators. Some actuators are automated, some are not. So we have to be able to configure according to the particular setting. And that means that we have to be able to execute these plans, sometimes completely automatically, and sometimes in collaboration with the human. So the way that that will work is that the plan will start executing, having planned everything, whether it's the human's activity or its own activity, and it will, where the activity is not something it has the means to control, it will simply wait for the signals to indicate that that activity is finished. So essentially the human at that point has the opportunity to follow the advice, if you like, that the system is giving it and do what they're expected to do. If they don't, what will happen is that the plan will time out. At some point, the sensors will detect, or what sensors we have will detect, that the system hasn't progressed within a certain time limit, and that will be interpreted as plan failure, and we'll replan and then offer a new plan to the driller. So it's not an explicit interaction, but it's an implicit interaction that follows from that kind of collaboration between the machine and the driller.
Hi, Eric. Thanks for a great talk. You mentioned the languages and representations and planners that you built on. Can you give us an idea of how much of the system that you have from a planning and representation perspective is actually taking things from the literature, and how much is stuff that you and Maria have kind of had to build since then?
So everything in that deployed system is standard PDDL. Standard PDDL planner. I mean, in 2016, that was POPF that was doing the planning, that was drilling holes, that was doing that stuff. Since then, we've built a planner inside Schlumberger, but it's PDDL. It's pure PDDL. And in some of the more recent things that we've been looking at, we've been thinking about ways that we might extend PDDL, but I like to think that we have stayed true to our original goals of retaining generic, domain-independent solutions to these problems. So every time we think about what we might want to be able to say that we don't see an easy or convenient way to say, we're thinking, what's the more general setting for this? Can we do this in a way that would allow the community as a whole to benefit from seeing these kind of language extensions? And our goal is to make our ideas on that kind of stuff available as soon as we have the opportunity to do that.
Okay, great work, Derek. Thanks. You mentioned the issue of confidence in the scripting approach, that it will do what it should do.
Yeah.
But given the complexity of PDDL models you mentioned, isn't there an issue of confidence as well, like PDDL validation, testing, etc.?
It's a good question. So the complexity of the PDDL models is when you present individual actions, the complexity is not that great. I mean, you're looking at an individual action. So the complexity is the emergent complexity from the behaviors that you can construct from those actions rather than from the individual parts of that description. And one of the things that's been really interesting is that when So I mean, we're not involved in this part of the process, but when clients are going to talk to the engineering team about deploying this system on their rigs, they care about, you know, what's going to happen on my rig, what are you going to actually do. And in order to persuade the clients that they can trust the system to do the job, what has happened and what usually happens is that a group of technical people from the client will come and have a workshop in the engineering center, and the engineers will go through PDDL models and say, these are the actions, do we all agree that these are the actions, these are the preconditions, and they will spend, I mean, the last time that I know that this happened, they spent a week with technical team going through PDDL actions line by line, looking at preconditions and postconditions to confirm that both sides were confident that that was a description of each of those actions. And once they see individual actions as describing what they anticipate that they should describe, they accept that the planner is doing what it's supposed to do. So they kind of accept from that point on that the planner is going to generate plans that they trust. So actually the confidence is built at that atomic level, I think. It's quite an interesting phenomenon.
Thank you very much, Derek. I think we have to stop here.